All right, let's start with this example here. We have a fan cart in the Wile E. Coyote configuration. Draw a free body diagram and explain how the fan cart will accelerate when the fan is turned on. All right, so the free body diagram's pretty good. We can look at sort of this uh, apparatus here or whatever. We can say that's our object that we're interested in here. We can draw, again, if we're drawing a free body diagram, just a box, that kind of. You can have a sketch or something like that that's a little more representative of the situation, but for a free body diagram, you just want a nice box. That's it. And so this is our Wile E. Coyote fan configuration. What are all the forces that are going to be on this thing? Well, we can say we know we've got gravity. We've got is on some sort of surface here. So we can say there's a normal force on this as well. And then we've got this fan here, right? So let's call this some sort of, we could look at this as an applied force or whatever. The fan is going to blow some air at the sail, right? And so that's going to apply a force in the forward direction. So we could call that the applied force or the force of the air molecules. And do we have any other forces? Is this thing going to move at all? More importantly, I guess, what is going to happen here? Is this thing going to move at all? Is it going to move forward? Is it going to move backwards? What do you think? Yeah, it looks pretty even just from the poll, but I realized that I probably may have misled people to forward because I drew in this one applied force like halfway through. I should have just done the poll first in terms of where it's going to go. But yeah, if we look at this, because there would also be something else. So you think about what happens here, and we'll get to it a little bit later in more detail. But when a fan, right, technically sends air molecules, right? So we've got air being pushed this way, while Newton's third law says, right, there's an equal and opposite force on the fan, and because it's attached to everything on him, right? So you could say this is the force from the air, right? This is the force. Oh, that's not a good way to write it. This is the force of the air on the fan, right? So you could say there's actually a reaction force here if you wanted. I'll just write FR for reaction, now this is where if this sail wasn't here, right, then this thing would just go backwards, right? The fan would blow the air forward, which would, again, Newton's third law would apply a force on this apparatus, and you'd actually go backwards. The problem is, though, there is a sail there, so the air molecules that have that force on them, sending them forward, they hit the sail, sorry, and that applies a force in the forward direction, and so as a result, this thing goes nowhere. Fun. A neat device to kind of look at or study. Okay, so this is a video here from online, which is linked on our course plan, and you can see it's just a fan, and it's moving forward. And then if you stick this sail in front of it and turn it on, he's going to turn it on in a second. Any second now, he's going to turn the thing on. There you go. And sure enough, it goes nowhere. All right, moving on. A silly physics student tries to absorb the material in their physics textbook by pushing their textbook into the wall with their head. Draw a free body diagram for this occasion. So the first question is, well, what should happen to this textbook if the student is, well, I guess, using their head and pushing it into the wall? Does the textbook go anywhere? Right. I mean, that's sort of our everyday experience, right? That this thing would go, yeah, wouldn't go. You can push something like a textbook into a wall. So yeah, we could draw. Again, I could draw a wall here. Usually, again, we just use some sort of line and give it a little tick, like diagonal tick marks like that. And I'll draw that. Here's our textbook. And so, what are the forces on this textbook? Yeah, we definitely got gravity. What about, do we have a normal force? Yeah, we have an applied force. We have a normal force. So the applied force then would be in this direction, right? It's being pushed straight against the wall. Uh, well, this thing's not going anywhere. So what has to balance the applied force? What's the force that has to go in this direction? Right? That's the normal force. Remember, the normal force is always perpendicular to the surface. So in this case, it has to be right that direction. And what's opposing gravity? Absolutely, right? It's friction. And there's our lovely textbook not going anywhere. All right, now we got one a little bit more work, but I just want to show you an example like this. So when you're doing problems like this, you've seen one with a little more math in it. So now we've got Mr. Brown, 80 kilograms, thereabouts. Likes to sit on a Jim's Pizza sign, which weighs 1,200 newtons. So that's kind of nice. We get the weight right in newtons. And contemplate his life choices. The sign is suspended by cables on both top corners at angles of 30 degrees above the horizontal. Determine the tension in the cables. Okay, so it's nice that it's the same angle on both sides. These should basically balance out. I would draw, well, I guess first I'll sort of define, I'll say this is my positive y, this is my positive x. I'll just do one box here to represent both me and the sign. So this is sort of my free body diagram representing the 2 and 1. So it's 1,200. I guess if I wanted to, I could look at myself as some sort of applied force. Right. So in this case, the applied force is the force of me on the sign, or the force of gravity pulling me down. There's different perspectives you can have on that, but I might look at it that way and say, well, that's 80 times 9.8, which is 784 newtons. So that's the applied force that I have on this thing. Obviously, then there's going to be the force of gravity on this sign because of its own weight. And we know it's already 1,200 newtons, so we don't even have to convert that. And we can say there's the force of gravity on this thing. Okay, now we've got the tensions in the cable. Right? That's basically the only other forces here. They're both at 30 degrees. So I'll draw them again just from the center, just for hopefully that's reasonably. So we can call this T1, or I guess if you prefer FT1, and this is FT2. We'll just separate the two tensions in these. And I would probably break these into components because my X and Y axes are right the standard ones or whatever. Then I would break these into components just so when I'm solving I can look at each dimension independently. And I can do the same thing over here. Now, I don't know what exactly these tensions are. That's what I'm trying to actually figure out. But I do know these angles here are 30 degrees. Right? So I can still write them in sort of a component form, right? Because this here, right, is basically whatever that value is. The magnitude of that is like the value that represents the length of this vector here, right? The actual number. So, oops, sorry. So that means I can look at this side over here, if you wanted to call that y, the opposite side of this first triangle here. And then I can say, well, I know that the sine of 30 degrees is going to be y over this side here. So that means I can rearrange that then and just say this is ft2 sine 30 degrees. And that means the cosine of that is going to be the one on the bottom. So I can say this is ft2 cos 30 degrees. And I'm going to get this same thing over on the other side. If I look at the first angle here, and I could do the cosine first, right? I could say the cosine of that 30 degrees is this side here, x, divided by the hypotenuse, which is ft1, and then rearrange that, and I get ft1 cos 30 degrees. And for the other side, ft1 sine 30 degrees. So yeah, I mean, and I do understand here some people might say, oh, well, like, couldn't I just sort of average these out or represent this as one tension? I know I do expect them to be equal. So let me be clear about that because they're both at the same angle. But in the next problem, the angles might not be the same, in which case they would be applying different tensions. So just good practice to say, I'm going to actually separate them out right now. Also, yeah, and there's nothing else pulling on this in the what I'm calling the x direction, but it's possible there is. It's possible someone else applies some force, let's say in this direction here, and then I've got to take that into account, and that's going to change the tensions in the cables. So good to take each thing that's applying a force and make it its own thing here. And then I can look at, like I said, I can look at each direction independently. If I want to look at the y direction, which I think is kind of the important one here, right? And then it's just a matter of making sure things that are positive, things that are negative. But also, and this is where static problems like this are really nice. I know this thing isn't moving at all, right? This sign is stationary. Hopefully, it's not falling when I sit on it. So that means the sum of all the forces, right? The net force has to be zero. And so basically, what you always do is you add up all the forces and that equals ma, right? If it's not moving, then a is zero, and that sort of helps. So we can say the sum of all the forces, in this case in the y direction, equals zero. And just so you know, this sign here means sum, right? It means add them all up, just if you haven't seen that before. And the zero again because it's not moving. So let's look at the first force in the y direction. That to me would be this first force of tension. So that'll be Ft1 sine 30 degrees. And then I'll have the same thing over on the other side. Ft2 sine 30 degrees. And these two FA and FG are in the negative direction. I've already figured out FA is 784, but I guess I could just write that minus FA minus FG equals 0. Okay. Sine of 30 degrees is just 1/2, right? So FT1 plus FT2 times 1/2 minus FA, which I think I said was 784, minus FG. And okay, this would be like, again, technically, I know I expect these to be equal, but I really could have looked at the, let's just see where I got some space here. Let's look at the x direction, because we only really have the two forces here. So we have FT1 cos 30, FT1 would be in the negative direction, plus FT2 cos 30 equals 0, because it's not moving, which means if you take that to the other side, you've got FT2 cos 30 equals FT1 cos 30. Certainly I can divide both sides by the cosine of 30, and I'm left with FT2 equals FT1, which again, I know for this problem we kind of knew anyway, but just good to work it out methodically, because if these angles were different, this would not be the case, and you would end up with some expression here for the relative proportion, right? And then you could go and substitute that in. Here it works out nice. They are equal, so I can just replace this here with, I can just say this here is just, I can replace that with FT1. So I've got a half FT1 plus a half FT1, which just equals FT1. And then I can add 1984 to both sides. And that's it. And since they're both equal, right? And that gives me the tension in both of these cables.